All right, so we are in BC Calculus. Today is lesson 1-4, our last lesson in our Unit 1, getting all of our basics down. Today's date is Wednesday, February 5th, 2020. Our objective is to do what, James?
Understand the properties
Yeah, and I could probably spend 1 to 2 weeks talking about how intriguing and interesting, that's the same word, it's a synonym, infinity is. We could talk about Zeno's paradoxes even more in depth. We can talk about all the videos that you're going to be having for homework. But I am boiling it down into one lesson to be done with it. So if I'm infinite, that means I do not have a, what? Say it with a quiet raised hand. Fiona? Louder, please. And yes. And then finite does have an end. Alright, so the first thing that I'd like to show you is that 0.9 repeating is 1. So this is I've done so many of these tasks before, I'm kind of curious. Do you guys remember me showing you the proof that 0.9 repeating is 1?
Yes.
Give me a thumbs up if you remember me doing that. So only one of us, and that's Arrow.
There's a chance it wasn't you who showed me, or you showed me.
But you know that 0.9 repeating. Okay, so how many of us, do a fist of 5, and I'm expecting most of you to be giving me 1s, believe that 0.9 repeating is 1? I trust you 5. I don't trust you 1. Because if I were in your shoes, and I was in your shoes, but I did this in college, not in high school, I was giving myself a very hard 1, like a 0 if possible, a 1. Like, there's no way. Like, that is an infinite number. That is a finite number. Finite cannot equal infinite. And this was a problem, I think it was proposed by George Cantor. I don't remember the year, but he's the guy that dealt with infinities, and his story is kind of cool. He thought about infinities so much. He's the person that thought of the infinite hotel that you guys learned about. And I think he eventually died in an insane asylum because he was thinking about infinities too much. Yeah, so you have these like fun little history things in math happening. But it's weird. So I'm going to prove to you with 2 different proofs that something finite can be infinite. Say again?
He was that obsessed about infinity.
I wouldn't say obsessed, but he was very well respected for his work on infinity. Although at the time when he was doing all of his work on infinity, people thought he was crazy. He was cuckoo. He was bonkers. All right, so my first proof. I'm going to just use fractions. So this is a proof that I would use on, when do you learn about fractions? Is that like 4th grade? So this is a proof I would use on 4th graders. So my proof is this. Do we agree that if I have 1/3, what is the decimal representation of 1/3? 0.3 repeat. And we should be using quiet raised hands, but that works. And I'm going to use this symbol, and Mr. Brown quizzed me on the name of that symbol, and I did not remember it. Does anyone else remember this name? We remember searching it up. All right, okay, we need to Google this.
Yes.
What does the bar...
Wow.
What is the name of the bar for repeating?
You searched it up before.
It's called a vinculum. Let's write it down in our notes. Maybe we'll remember it.
No.
This symbol, right? Maybe I should have the arrow pointing to the right thing. It's called the vinculum. And I get really cringy whenever I this is a vocab word. It's like, yeah, humans have decided to call it something, and I guess that's a good thing. If you call it bar, we all know what it means. It's the same idea behind, oh, what is this symbol called? Oh, it's a hashtag. Well, technically, it's called an octothorpe, but if you call it an octothorpe, no one's going to know what you're talking about. Anyway, we can all nod our heads yes. We have a 5 out of 5 understanding. 0.3 repeating and 1/3 are the same number. Do we agree? Well, that's a problem, because you have just told me something infinite equals something finite. But let's go ahead. You guys still believe me. I have your 5 out of 5 understanding. Something infinite does equal something finite. It's this weird thing that we've taught you that it happens, but it's uncomfortable because that has some interesting properties. So I'm going to multiply both sides by 3. Times 3. Times 3. When I multiply both sides by 3, it is not 0.3 repeating, it is 0.99999, so a 9 with a vernaculum above it, is equal to 3/3, and that I can just write cross cancel, and 3/3 is just 1. All right. I would like my applause now. Thank you. Thank you. Oh, that was hard. Well, do you believe me now?
That's alright.
I just proved it to you. If you believe that 1/3 is 0.3 repeating, I just multiply both sides by 3, done. 0.9 repeating is 1. 0.9 repeating is 1. Maybe if I bombard you with proofs, you'll believe me. I don't know. Let's try another proof. Ta-da! Proof 2. Let's assume that x is equal to 0.999, etc. repeating. Again, I'm going to manipulate this expression. I'm going to multiply both sides by 10. 10 will move the decimal place, so 10 is a good number to multiply by. So times 10 times 10. Our new line down here should say, well, 10 times x is 10x. We nod our heads. 10 times x is 10x. That sounds good. And 0.9 repeating, I can now move the decimal place 1 to the right, so it's 9.99999. My 9s get sloppier and sloppier the farther I write them out. 9 repeating. Everyone nod your heads. That sounds good. Have I done any tricky things yet?
No.
Okay. So I'm going to now subtract x on both sides. This is where this is like maybe the hardest part of this proof. So if I subtract x from 10x, I'm left with, dear gosh, if I have 10 of those x's and I took one of those x's away, if I had 10 apples and I took one apple away, I'm left with 9 of those x's. Yeah, so I'm saying subtract x and I get 9x. I'm going to subtract x on the right-hand side, but here's my thing. I'm really subtracting x, which means I'm subtracting 0.9 repeating on this side. We assume that x and 0.9 repeating are the same thing, so I can subtract x, or I could have said subtract 9 repeating here. So I'm going to choose to subtract 9 repeating on this side. So subtract 9 repeating. Subtract 0.9999 repeating, and check it out. So 9, 9, 9, all of those cancel each other out. I'm left with 9. Finally, we have to tidy up a little bit and we say, okay, divide both sides by 9, divide both sides by 9, and x is equal to 1. But wait a sec. So does that make sense? We subtract the x on both sides. That's allowed. Divide both sides by 9. Division is okay. X is 1. Okay, what does that mean? Well, x is 1, x is 0.9 repeating. These x's are the same thing, therefore 1 and 0.9 repeating must be the same answer, and that is my conclusion down here. If those x's are the same thing, therefore, let's do a little therefore symbol to be very formal about our mathematics. The therefore is the 3 dots in a triangle. Therefore, 0.9 repeating is equal to 1. And by the way, if you're doing a proof, these are proofs by the way, you always end with a QED, or you can do a little, I like ending it with a filled in box. Filled in box to let you know that you have finished your proof. QED is Latin for quorum et deternum, which basically translates in I have proven what I needed to prove. There's 2 proofs. And all mathematicians agree that 0.9 repeating is 1. If you don't agree with that, you need to disprove it to me. If you can disprove it to me, you'll probably get like money because everyone in the mathematics community agrees that 0.9 repeating is 1. And there are lots of reasons. I just gave you 2 simple little proofs. I can give you a lot of reasons. Instead of me giving them to you, I'm going to let a YouTuber do it. Her name is Vi Hart. I think her first name is Victoria, last name Hart. Daughter of George Hart, who's also like a mathematical artist, I guess. You remember the pencils that I had that like randomly fit together?
Yeah.
George Hart did that. So his daughter, Vi Hart, is very famous on the interwebs. And she has a video that you'll see in the homework tonight where I think she said something like 99.9 repeating % of mathematicians, 100%, agree that 0.9 repeating is 1. It's a really cool video. And your homework, one of your homework questions tonight is make your own proof. You can't use my proofs. I've already taken them. So she goes through 10 proofs. You have 8 of her proofs to choose from to copy down. And I've watched that video now like 10 times. Every single time I rewatch it, I get something new. Like this last time when she talks about her 9.9 repeating Lords of Leaping, 10 Lords of Leaping from the Christmas song. Each of the Lords is like Lord Vader, Lord of the Flies. They're like all different Lords, and she draws each of them. It's pretty cool. But she talks even faster than I do because I think she just says times 2 when she makes her videos.
John Green fast? Or fast?
It's pretty.
All right.
Usually we.
I bet you will think it's too fast. Anyway, these are the properties of infinity that you have to have down by today. Your self-checking stuff is going to be like a multiple choice, like which of these is equal to infinity or 0, basically. So, if I have a number, 10, 5, 2.9, pi, whatever, a number plus infinity, that's infinity. So what's infinity plus 1? Infinity. So if you think infinity plus 1 is bigger than infinity, you're wrong. It's the same infinity. If I subtract infinity from a number, it's basically saying you can assume that number is 0. 0 minus infinity is negative infinity. So 200,000 million minus infinity is still negative infinity. As long as I multiply a positive number, so I said positive by saying, oh, n is bigger than 0, but if you want to add in your notes, you can say n is a positive. That's a bad plus right here. N is a positive. This n is a negative because n is less than 0 means negative. That means positive. If n is less than infinity, if n is positive times infinity is positive infinity. Negative times infinity is negative infinity. N to the power of infinity, as long as n is big, like bigger than 1, then that's infinity. Infinity to the power of n is infinity, as long as n is bigger than 0. And when I divide n by infinity, I get 0. These are all the properties that we have to have memorized. And I'm going to be throwing you little tricks in there. I'll be like, for what values of n does this hold true? And you'll have to remember, oh yeah, bigger than 1. Why? Well, let's think about this. If I do point like a half, if n is a half times a half is a fourth, times a half is an eighth, times a half is a 16th. I'm basically going not to infinity, but to 0. And why does n have to be greater than 0? Well, if n was negative, then I would be flipping it. So I have to be really careful about my negative powers because that means flip, and that means something totally different. Those are your properties. And that's basically the end of the lesson, but I wanted to have some really more fun. So that's all of the BC Calculus material that you need to know, but I want to show you some things that are not going to be on the AP test. So I'm not going to quiz you on anything, but I want us to know this because it's things that I wish I knew when I was going into college about mathematics. So in Weihart's video, she talks about how there are different sizes of infinity, and she even goes into quaternions and a bunch of really cool mathematics things that I didn't even study when I was in college studying math. But I want to teach you about the basics of sizes of infinity. So, reveal, there are different sizes of infinity.
Why?
Great question. That segues into my next part. So, the lowest, the smallest type of infinity looks like this. It looks like a sideways Z, and it's nice and curly. It's called Aleph Null. 0 is pronounced null, so you don't pronounce this Aleph 0. It's Aleph Null, or Aleph 1, Aleph 2. By the way, Aleph is the first letter in the something alphabet. Not Greek, is it? I think it's some Middle East language. I really should know that. Anyway, Aleph Null is the smallest size, and it represents the natural numbers. So whenever I have like the bold script like that, that means natural numbers. And mathematicians actually do not agree on what natural numbers are. And you can have your own definition. Is 0 a natural number, or is it not? And that's the main distinction. It goes 1, 2, 3, 4. Some mathematicians include 0, some of them don't. But generally speaking, natural numbers are your counted numbers, things that we've always had with us as long as we've had fingers, right? We can count, okay, I have 2 grapes, those are natural numbers. When I get to decimals, that's maybe later when you're like talking about Egypt and stuff like that, when you have those numbers. So natural numbers is the definition of the size of the smallest type of infinity. So let's talk about integers now. Integers are whole numbers still, but also negatives. And zeros are included in there now. So -3, -4, -5, all the way up to negative infinity. 0, 1, 2, 3, all the way out to infinity. And I'm going to tell you that also is Aleph Null. It has the same cardinality. And you might be thinking, hopefully you're thinking, shouldn't it be 2 times Aleph null? Isn't it twice as big? I mean, I have one direction and then 2 directions. It's going out to infinity in 2 directions, so it should be twice the infinity. You can hopefully nod your heads. Yeah, that makes sense. No, you're wrong. I'll show you why. Because the weird property with infinity allows us to do certain things. Remember, the definition of the cardinality of Aleph null is the natural set of numbers, which means in order to prove that the integers have the same cardinality, I need to somehow write the natural numbers. So the way that we write natural numbers, go with me. Natural numbers is equal to, I'm just going to assume, I'm going to start at 1, 2, 3, 4, 5, on and on. We know that the next number is 6. The pattern is clear. Once we see the pattern, I'm going to stop. I'm going to prove to you now I can turn 2 infinity directions into 1. How do I do that? And here is the cool little answer. I'm going to now rewrite our natural numbers, or not our integers rather, as 0, 1, -1, 2, -2, 3, -3, and I'm going to stop right there because I think the pattern is pretty obvious. I just reordered the numbers a little bit. I've changed it, instead of going out to infinity left and right, I'm only going out towards infinity on the right, just like natural numbers. And this is the general procedure. I'm going to, technically mathematicians call this mapping. I'm saying, hey, check out how 0 and 1, 1 goes to 2, -1 matches to 3. These all match up. 3 would go to 6. I can match up as many of these integers as these natural numbers. Therefore, since there's an infinite number here, infinite number here, and I match them all up correctly, these sizes must be the same. And if you still feel like, oh, this is still twice as big, I mean, I understand where you're coming from, but I have proven to you now that integers and natural numbers have the same cardinality because I've matched them up. Yeah, Joe. I have to somehow link each of these 1 numbers to one of these numbers. I can't say 0 is equal to 1, 2, and 3. It's just the way that you map one set onto another. I have to link up numbers. But generally speaking, I didn't even have to do that. As long as I can show you that the list goes in one direction, just like natural numbers, then I have proven it to you. All right, so I'm going to try to prove it to you for fractions. That seems way harder. You're like, wait, fractions? There's an infinite number of fractions. How am I going to get 57/39ths? That's a fraction. How am I going to get 100 over 1, which is a fraction, 100? How am I going to get all of the numbers that are fractions? Things that are not fractions are like pi and e. But how am I going to get all fractions in a list? Anyone have an idea? It's hard. It's really hard. And the answer is I'm going to make a 2-dimensional list and then turn it into a 1-dimensional list. So here we go. Bear with me and then we can do the video. Let's start with the fraction 1 over 1. For this row here, I'm going to make it so that the only thing that increases is the denominator. So this next number is going to be 1 over 2, then 1 over 3, then 1 over 4, then 1 over 5, etc., etc., etc. So I'm going to just do ... The pattern has emerged. We know what's going to happen next. That's my first row. For my next row, I'm going to change this to 1 over 2. Sorry, not 1 over 2. 2 over 1. I'm going to increase the numerator by 1. And then this is going to be 2 over 2, 2 over 3, 2 over 4, 2 over 5. Okay, I think the pattern has emerged. All I did was I increased the numerator by 1. All I'm doing right now is I'm trying to list. I'm trying to show that I can create a 2-dimensional list of all fractions. Every single fraction ever imaginable. All right, the next one is going to be 3 over 1, 3 over 2, 3 over 3, 3 over 4, 3 over 5, etc., etc., etc. Anyone want to take a guess at what the next row is going to be? You can shout this one out. 4. 4 over 1. 4 over 2. So I think the pattern has now emerged this way. I'll just do a few in case you didn't see it. 4 over 1, 4 over 2, 4 over 3, etc., etc. And then down this way as well, this is going to be 5 over 1, etc., etc., etc. So that's how I'm going to make my table. So the question that I have before I do the proof is, do you agree going out to infinity in this direction and in this direction, this list will include every single possible fraction in existence? And it will. Hopefully we see that. Does anyone still feel unsettled by the fact that I've listed every single fraction? Okay. And then how do we list these in an order? I need to convert this two-dimensional list into a one-dimensional list. And here's the answer. Just go diagonally. So I'm going to start by going through 1, 1, then 1, 2, 1 half, then 2 over 1, then 3 over 1, 2 over 2, 1 over 3, then 1 over 4, 2 over 3, 3 over 2, 4 over 1, then 5 over 1, 4 over 2, 3 over 3, 2 over 4, 1 over 5, etc., etc., etc. Do you agree that if I was listing off these numbers one by one in this order, that I would be listing off every single fraction in one giant list that goes only in one direction out to infinity? The answer should hopefully be yes. I have now proven to you that all rational numbers also are of the size aleph null, or of the cardinality aleph null. Cardinality and size are the same word. Cardinality is the official word that we use. So I'm going to give you guys a challenge. I decided to give you extra credit for just throwing in an extra bone, but I'm wondering if you guys would be able to disprove one of the other ones. Real numbers, the set of real numbers, so 1.35987 or e or pi, anything that, as long as it doesn't have imaginary numbers, anything is fair game now. Can you prove to me that those actually have a higher cardinality than all the ones that we've been talking about thus far? That they're not able to be put on a list that goes out in one direction? So if you even look up a YouTube video or look up something online and you just copy it down, I'll give you the extra credit. I'm just curious who also has the same curiosity that I had when I was in high school, and I'll give you a reward for it. I'll give you some extra credit. So just go online, prove to me that the set of real numbers, this bold R, does not have the same cardinality as the ones that we've been talking about. I'll give you 5 points of extra credit if you do that.
Can I write it in my summary?
Your proof is going to have to be more space in that summary. Proof is a little bit longer than what I just did right here. All right. So that concludes this lesson. I want to go ahead and start working on the YouTube videos right now.